Hi everyone, thanks a lot for coming. Thanks a lot ADC for having me. And today, so as introduced, we'll talk about antiderivative anti-aliasing for wavetable synthesis. So let's introduce. First, I'm Maxime Coutant. I'm an audio software developer. I work in the ADAS research group, which is part of the LTCI public research laboratory in Telecom Paris in France. And today I'll be presenting a hobby project of mine. And I'd like to make a few disclaimers. First, this is not a research talk. I try not to delve into too much of math details. We're going to talk about a research paper. If you really want to know the details of the paper, I highly encourage you to check the paper itself. You'll probably understand it better than if I try to explain it to you for 40 minutes. Also, this is not a practical guide for wavetable oscillators or anti-aliasing for wavetable oscillators. If you want a practical guide, I highly encourage you to check my title's talk from ADC23 2 years ago. There's a QR code for that, and there will be a few QR codes for most URL in this presentation. Okay, so quick outline. First, I'll try to introduce what we're actually dealing with, so everyone start on the same basis. Then we'll talk about a research paper and its results, and then what I did with the research paper and the results that came out of it. Okay, so first, let's settle things down. Oscillators, what are oscillators? The oscillators are tools. They're used to generate a waveform at a given frequency. The frequency can vary, can be steady, it can vary extremely quickly. It's kind of the basic block of tonal audio synthesis. The waveform itself can be what I like to call basic waveforms, so like the one you can see, so sine, square, triangle, sawtooth, which are kind of a legacy of how analog synthesizer. But technically, they can be arbitrary. You can generate them using math function, using lookup tables or samples. You can do pretty much anything you want. Okay. So what's more precisely a wavetable oscillator? The idea of a wavetable oscillator is that you have a waveform that is loaded into a table, so a buffer, mainly have samples of it, and you have phase value of the output you want to produce, or frequency value, it depends on the way you implement it, and you have some kind of interpolation algorithm, and you produce the output value. I'm not like super good with visuals, so I'm sorry for that. Graph are not aligned and everything, you'll see. Okay, what's aliasing? Aliasing in the audio world occurs when you try to represent frequency that are above your Nyquist frequency, which is half your sample rate. So here you got kind of a quick example. So you have a signal with its fundamental in blue, you have its harmonic in green, and you have in dotted green the harmonics the signal should have. But since they're above the Nyquist frequency, if you still try to represent them using your sample rate without trying to get rid of them, then you'll have the orange spike that you can see here, which are what we call aliasing. These are unwanted harmonics that fall back into your audible spectrum. Also, if you want to know more about anti-aliasing, Sam Fisherman made a really nice talk earlier. So what's about oscillator and aliasing? Well, first, let's talk about waveforms. So almost all basic waveform you saw here, like saw wave, square wave, the perfect version of them have theoretically an infinite number of harmonics. So if you try to represent like a perfect version of this waveform, you will necessarily have harmonics going above your Nyquist rate. So you will have harmonics, whatever you're trying to do. But even if you use like a waveform that is stored into a buffer, so by definition it has a discrete number of points, so it has a discrete number of harmonics. Well, if you pitch it up higher than the sample rate it was recorded to, what will happen is some of the harmonics can go above your Nyquist frequency, and then it will introduce aliasing. Okay, another illustration real quick of aliasing with oscillators. So this is a sweep test using a saw wave. On the top, you have like a really naive linear interpolation algorithm with no anti-aliasing at all. And at the bottom, you have like really strong anti-aliasing with oversampling by 32. It's simply to illustrate what I've been saying earlier, is that if you look at the harmonics on the upper graph, you see that when they reach the Nyquist frequency, they bounce back, creating this symmetric pattern, kind of like the moire pattern you would have with graphic aliasing. Okay, so how do we deal with anti-aliasing, with oscillators? So I'll cover a few techniques. First, there's what I like to call band-limited techniques, so either BLEP or BLIT, which are based off, you need to have kind of an analytical version of your waveform, and the idea is you'll try to remove the discontinuities or to smooth that out. But if you have an arbitrary waveform, what you can do is rather using FFT band limiting. So once again, if you're interested in that, check my title talk 2 years ago. It was amazing. Another technique you can use is oversampling. So the idea of oversampling is simply that you will temporarily use a higher sample rate, and doing that, you kind of push further away your Nyquist frequency. So you can try then to attenuate every frequency that lands between your target Nyquist frequency and the oversample target frequency. Another thing that you can do is what we tend to call MIP mapping. It comes from the graphic world. And the idea is you will downsample several times your waveform to have a version of your waveform with less point, therefore less harmonics, and that you can use when you're pitching your waveform up. Therefore, it has less harmonics going above your Nyquist frequency. So if you try to illustrate what MIP mapping looks like, here is a waveform, and on the top left, you got the original waveform with 2048 point, and then you have like the same waveform downsampled here by a factor of 2 several times to get the same waveform, but with less point each time. Okay, a last contender that I like to introduce is antiderivative anti-aliasing. So here we're not necessarily talking about oscillators. It's a technique that was introduced in 2016 by a team of 3 people from Native Instruments, so Julian De Parker, Vadim Zavalishin, and Eflam Lebevik. Sorry if I mispronounce the names. And the idea of it is that you want to anti-alias usually a non-linear function, and you work with the analytic version of your nonlinear function. And you will anti-differentiate your function 1 to several times in order to virtually go to a continuous domain. So it's kind of like oversampling, but rather than going to a domain with a Nyquist frequency that is further away, you virtually go to a domain where you don't even have a Nyquist frequency. And then you filter it and you go back to your discrete domain. So here is a quick formula. You don't have to understand it. Simply, this is usually how you will represent first order, in the meaning that you anti-differentiate only once. And this is, also first order antiderivative anti-aliasing, and the big F is the first antiderivative of your function F that you're trying to anti-alias. So it was first used for a bunch of nonlinear processing methods, and it was mainly using FIR filters with like really basic kernel, because the idea is that you have to be able to anti-differentiate the kernel itself, so it has to be a bit simple, at least from what I understand about it. And it could use 1 to several orders of differentiation, but the complexity could rise with the number of anti-differentiation orders. What about me in all that? Well, I have a hobby project. It's a software synthesizer. I wanted to implement a wavetable oscillator in it, so I went on Discord and asked, okay, how can I do like anti-aliasing for wavetable oscillator? I don't want to use FFT band limiting, so I spoke with a bunch of people, and I was told about antiderivative anti-aliasing. So I looked a bit, but I couldn't find like a working implementation for oscillators. So I went a bit deeper, and I found this paper called Antiderivative Anti-Aliasing for Arbitrary Waveform Generation. And then I went down the rabbit hole, and today I'd like to bring you with me in this rabbit hole. You'll see, it's cozy. Okay, let's talk about the paper now. Okay, so the paper, I already tell this name. It was written by Leonardo Gabrielli, Stefano D'Angelo, who might be in the room with us. I saw it. Yeah, he's there. Pierpaolo Lapastina and Stefano Squarcini. And it was published in August 2022. It's freely available on the internet. You can scan the QR code to access the paper. And in the paper, I won't cover every details, but they mention existing techniques. So they recall it ADAA FIR for FIR kernel-based. And they also mentioned another approach they published in a previous paper using IIR filters. And they push it further away by proposing an algorithm for waveform generation. And also in the paper, they compare ADAA FIR with another technique, which is called DPW, I won't really cover that in detail, but they kind of prove it's equivalent. They proved it's equivalent. Okay, so let's talk about ADAA IIR, and I tried not to pronounce that too many times, it's hard. The main thing that's interesting about it is that it allows to use a wide range of IIR filters, including but not limited to Butterworth, Chebyshev, elliptic, so that's good. We have more choice than with FIR. And they deduce kind of a general equation for a nonlinear function f. Again, you don't have to understand the equation. You simply have to notice a few things. First, it's a recursive equation because we use a recursive filter. And also, we're working in the complex domain, so using the complex poles of your filter, which some of you might know, every two order, they are conjugated. So it's like approximately the same value. And we'll use that. Okay, so more specifically, how do they try to use it for waveform generation? So the idea, the trick, is to consider your wavetable as a piecewise linear function. And linear function is like easy to achieve differentiate. So you have the big X are like the point in your waveform, the samples you have in your waveform. It works with like waveforms that are not even sampled continuously. Like you can have points anyway. And locally, it's defined by M, X plus Q. M and Q are the actual values we're going to use in the computation. And I will try to illustrate broadly how it works, like the big part of it. So here you got in blue a waveform with the sample points in it. In orange is the last sample you have to produce, because remember it's recursive. And in red is the new sample you have to produce. And the way it works with the orange value, the red value, and all the point in between. So here you can, I don't know if you can see, we identify Imin and Imax, which are like the beginning and the end of all this part between the 2 points. And then big scary stuff. Okay, you don't have to understand this thing, simply notice it's called I, and this is like the biggest part of the algorithm. And this has to be computed for every point you have to produce. The big thing to note is what I try to circle in red, is we got a sum going from Imin to Imax. Remember all the point between two samples you had to produce, and inside it has a complex exponential. So we can easily identify that this is going to be the most expensive part of the whole algorithm, because a complex exponential is like really hard to compute. It takes time, and we have to sum several of them. Another thing that I didn't note here is that you have to compute this for every two order of your filter, but most of the computation is the same. Okay, so what are the results they present with such kind of thing? Because they had an implementation. So here is a sweep test they made with a waveform. We don't really care, it has stuff in it. And here we have 5 contenders. We have the trivial linear interpolation, or LERP for short, then LERP with 2 times oversampling, LERP with 8 times oversampling, then the version 1 of the algorithm, we'll call it version 1, using a Butterworth filter of order 2, and a version 2 using a Chebyshev type 2 filter of order 10. So it's have like really steep roll-off. What you can see is that the version 1 of the algorithm doesn't perform like extremely well, and it's kind of expected because Butterworth filter of order 2 is like not that much of a good filter. But the version 2 of the filter actually seems to perform like extremely well. For the record, the lower the threshold for the spectrograms is like minus 80 dB. If you compare it to the oversampling methods, one thing that you can notice is the oversampling method have more of a noise floor, and this is because of oversampling. Obviously, it's the noise floor comes from all the frequencies that goes above your oversample Nyquist frequency, and these are the ones you cannot alias, and they come back creating this blurry noise floor. Okay, another test they made was using SNR. So SNR is a metric that stands for signal to noise ratio, and it's kind of it's the ratio between the power of your fundamental and the power of the noise, and you exclude all the harmonics that are supposed to be part of your signal. Since we're using a saw wave because it's a good waveform for anti-aliasing testing, we'll exclude all the harmonics because it has all its harmonics. So here you can see a few contenders. You have DPW, 2 meters of DPW and 2 meters of AA FIR. So they're just demonstrating that it's the same. And what you can see is that the version 2 of the algorithm really outperforms by far anything else. Then you have oversampling by 8, which is really above. And then you got oversampling 2 and the version 1 of the algorithm, which are like not that great, but they're there. It works. Okay, so what can we say so far about the algorithm? First, it seems promising. It has a good SNR test, it has a good sweep test, but a few things to note. In the SNR test, they limited themselves to the frequency of a pioneer range, and also the SNR, because it excludes harmonics, is a metric with limits, and we'll illustrate that later. A few good points that we can identify. First, using complex pole, the way it's used, it allows to easily compute two orders of the filter at the same time. And the second thing, and sorry Stefano for that, but it's really important, really interesting for this algorithm, is that we can use a SIMD to compute several orders at the same time. And so we can expect that to compute a lot of orders of the filter at the same, for the kind of the same cost. Some bad things to note, though. There's this complex exponential in the ISUM, and another thing that some of you might have noticed is that the number of complex exponential we have to add in the algorithm depends on the frequency, but the frequency grows exponentially with the pitch. That means if we let it like it is, it has a cost that grows exponentially with the pitch. So we have to implement MIP mapping in order to reduce the number of points in the waveform in order to have like an upper bound of the computational cost that is reasonable. Otherwise, we'll have to go up maybe sometimes to 1,000 complex exponential to compute for each sample. That's not something you want to do. Okay, so now it's time to practice. Let's try to make things work. So when you go from research into practice, you have to settle things down. You have to decide what you're going to support, what you're not going to support. So in my case, I'll use Python for prototyping and C++ for benchmarking, speed benchmarks and stuff. I'll assume evenly spaced sample point in the waveform, and I only work with waveform of a size that is a power of 2. Then the first step will be to reproduce the results, and I'll spare you the details. Then the idea is to make it real-time compatible, because in the code and the algorithm they provide, they're using phase that grows continuously and an index that ever grows. So we have to implement some phase reduction and some index reduction, otherwise it will overflow and lose precision, and it will take more time. I won't go into the details of that either, it's not really interesting. Then we'll have to implement MIP mapping, then we'll have to find a way to benchmark. I won't cover that either, just pick to a benchmark. And then I'll try to optimize it with a SIMD, because I think that's one of the strengths of the algorithm. Okay, so let's talk about MIP mapping. In my case, I decided to use one waveform for each octave, so I don't sample by 2 every octave. And quickly enough, we can notice that we need to do crossfading between MIP map tables, because, so I don't know if you can see it, probably not, sorry. So here we got a sweep test of the MIP mapped version of the algorithm, but without crossfading. And at the transition point between the waveform in the circle in red, you have like little spike, and these are clicks. And this is because if you transition abruptly from a waveform to another that has a different number of points, therefore a different number of harmonics, you'll have either a sudden jump or a sudden drop in harmonics. So this will create a click. So we need crossfading. Okay, we know we need crossfading, but first we have to determine how to crossfade and then when to crossfade. Why how to crossfade? Because, there's an important point. There is an important point here to note. We cannot really allow to jump between any waveform in the MIP map table, because it would cause the worst case scenario we're trying to avoid in the first place. Let's picture that you go suddenly from one of the lowest frequency to one of the highest frequency. If you want to crossfade between the two, you'll have to compute at a high frequency using a small waveform, that's okay, but also a really big waveform. And that's what you want to avoid in the first place. So you have to choose what you're going to support. So in my case, the trade-off I picked was I don't allow for jump over MIP map table. I only allow transition between adjacent octave in the frequency range. And so this is kind of a strong assumption, because it means the frequencies variation of the algorithm are limited by the computational cost of it. Bit more details. I didn't went for a more classic time-based crossfade, but more of a frequency-based. So what that means is I pick a ratio 1, like ratio k between 0 and 1, and that actually is the proportion of each wave, mipmap waveform that is crossfade by the previous. I don't have like a really strong opinion on that. It was simply the fastest to implement, so I went to this. Okay, now we know how to crossfade. We have to decide when to crossfade, because you don't want to jump to another mipmap waveform at a point where it would make you lose quality because you have a waveform with less precision. So to decide when we want to transition, we need a reliable metric to tell us that we're not losing quality. And the only metric we had so far is SNA, and SNA is extremely bad for that because remember, we're excluding all the harmonics for the computation. And so when you go from a waveform that has more point and more harmonics to a one that has less point and less harmonics, because it has that harmonics, it will have necessarily less aliasing because less harmonics going above your Nyquist rate. So if you only look at SNA, going to a waveform with like less precision will always give you a better SNA. So I had to pick another metric that actually compares your signal to a perfect version of your signal and generate a perfect version of the signal. So here you're generating a perfect saw wave using additive synthesis. So I have like a perfectly delimited saw wave. So if we take a look at how it works with SNA, this is simply to illustrate what I was saying. So I don't know if you can see. So here is the SNA of like a big frequency range of using not mapping, simply waveform of different size. And you can see, I hope you can see, that the waveform with less point always outperform all the others because it lasts less harmonics. But if we draw the same graph, but with CNAD, then we got what we want. You can see that at first, the waveform with less points actually perform like really badly. And there is a point where they reach the same level at every other waveform. And that's where we want to transition. So here what I did is simply pick a first interesting point to transition and then added an octave later each time because I saw it kind of match. Okay. Now the algorithm is working. I had a working version so far, so let's try to optimize it. So I decided to use XSIMD, which is a C++ library for like really easy cross-platform SIMD implementation. On AVX2 mode, it offers me 128 bits, which is kind of weird, but that's what it offers me. So with this size, we can expect to run 8 orders of a filter for approximately the same cost. If you add FMA3, which is like an extension of AVX2, and I think it's available on most Intel computers nowadays, it goes up to 256 bits. So we can expect to compute 16 orders of a filter at the same time. And on Neon, so the ARM and SIMD extension, it's 128 bits, so more like 8 orders at the same time. And for that, for the record, for now, I only optimize the core of the algorithm, so the I computation, because this is the most important part. I didn't really care about the rest. Just drinking a bit. Okay, so now let's try to see the results. First, a sweep test. So this is the same sweep test, so a saw wave, 5-second sweep test. On the top, you have a naive linear interpolation with no oversampling, then the same with 8-time oversampling using the Psi-P decimator. Then you have a mipmap version of the version 1 of the algorithm, so using a Butterworth filter for the 2, and then the same but with a Chebyshev filter for the 8, not 10, because of SIMD optimization, I wanted to check how it performed because it will probably be more interesting than an order 10. So you can see that it seems to perform really well. It doesn't have this noise floor. It's even better than the one in the algorithm because we're using mip mapping and it improves performance, quality at least. And then an SNR test. So I'm still using, this is Python code, but this is calling the MATLAB SNR version. So it seems to perform like really well. Once again, yeah, higher is better with SNR. And the kind of weird thing to note is that the Chebyshev filter of order 8 seems to perform better than the order 10. I don't know why, but I checked the results. Both seems to be working well. So yeah, I'm fine with it. But if you have an idea why, I'll be happy to hear. And then let's try to benchmark. So I benchmarked using a linear sweep of 5 seconds, and I computed the average over like a block size of size 16 to 2048. So this is using my Intel CPU, only enabling AVX2. So we got kind of what we expect. Also, yeah, I compared it to the oversampling method in Juice. So I think it's SIMD optimized, and I'm using an IIR filter in max quality. So you can see kind of what we expected. So order 4, 6, and 8 take approximately the same time. Order 8 is a bit slower, but so that fits the expectation. And order 2 is not a SIMD at all. It's like simply scalar. So it's good because it seems that it's not really that slower to oversampling, so we're kind of the same realm, so it may be interesting to take decisions. Same thing with AVX2 plus FMA3, and then once again it matched the expectations because order 10 is now taking approximately the same time than order 4, 6, and 8. And here is a test on a Raspberry Pi 3, so I wanted to test a norm to make a norm test. And so once again, fits expectation. Order 4, 6, and 8 take approximately the same time. 10 is really slower. And on this implementation, at least, it looks like it's even faster than oversampling by 8 by Juice. Quick thing to note, if you check the code after, for now, the ARM version is broken because there's a bug in XSIMD, although the results are broken, but it takes the proper amount of time. Simply there's a sign switch into the exponential computation. And I think that's kind of all for the benchmark, so it seems to be working well. A few caveats and notes. I'm not like super confident with my CNAT computation, although I'm confident it helped me pick the good transition point. Don't rely too much on the CNAT computation. That if you know how to compute that properly, I'd be happy to hear. Also, usually, at least with FIR version of antiderivative anti-aliasing, it's often used in conjunction with oversampling. In that case, I made a few tests. It's probably overkill. It doesn't take advantage of the SIMD because the algorithm is recursive, and also like simply a butterworth filter of order 2 with oversampling of order 2, like really beat any version we've seen here, but we already reach a point where it's probably already a bit overkill. Also, my SNM measurements are good, but not as much in the paper, yet they're really good. And there's like this limitation of playback speed variation. These are hard to measure. A more classic time-based algorithm crossfade algorithm could help, but for now, it's not there. What could be improved in the future? We could investigate for fast math approximations, so exponential, sine, cosine, although I think there already are some in XSIMD. Also, it could be interesting to pick the best IIR filter for each order. I don't know much about DSP filter design, so I didn't went into that territory. Also, around 50% of the time, the ISM has 2 members in it, so maybe that could even be parallelized when you have enough room in your SIMD registers, so either order 4 or order 8, depending on the register you have. Maybe optimizing the rest of the algorithm. I tried to pick good decisions, but you can probably tweak a bit. And maybe there are some math tricks in the algorithm, in the math algorithm that I don't know about. Finally, I have to have a few words about crossing engineering and research. First, about academics. Please make sure your demo works. It happens quite often and there's some bug. I understand you have deadlines and stuff, but don't hesitate to ask for help if at some point it's buggy. Like it can really slow down the adoption of what you're doing if people cannot easily reproduce what you've been doing. Also, a good software environment helps research. I work all day with PhD students, postdocs, and having a good software environment for them help them focus on what's important, research, not like computer science shit that we have to deal with as engineers. And if you want people to work with what you produce, make your work accessible. For engineers and developers, you can help set up a good software and research environment. You know how these things work. Continuous integration, unit tests, Git stuff. You can help set up and foster the collaboration. Also, if you have to deal with MATLAB code and you don't have a MATLAB license, there's Octave, which is a free software interpreter. It has mostly compatibility. And finally, please double check your vocabulary. It happens like quite often that you use the same word but with different meanings. Finally, it's alive. I tried to share my code, so the Python experimentation is there, the C++ library as well. It's supposed to be real-time compatible, easy to add new filters, MIT license. I haven't had the time to make really good stuff. Remember, it's like a hobby project, so I don't have CI and proper good unit tests, only reference tests for now. And we also have an open audio engineer position at Adaps, and here is the website if you want to check. We make cool research stuff, mostly deep learning based, but we make cool stuff. And I'd like to address finally a few thanks first to the audio programmer Discord community that has been extremely helpful, and more especially to Jaren from Signal Smith Audio, Matthias Halsman, and sorry if I may respond on that, and Matthias Stillen that helped me wrote the ADC abstract. Thank a lot for you all for your time, and please tell me if you have any question.